已解锁，请起出话筒。
While waiting for the rest, I think they need 5 more minutes. Maybe you can try this question in your lecture notes. You can try this question. Then later we'll briefly discuss and then we'll make a summary for multiple integral and then we'll go into vector functions. Sorry. Okay, we'll try. So let's quickly discuss it. So this is a warm-up for your last part of your multiple integral, where we can do addition of variable to compute your integral. Okay. So in this case here, you are asked to integrate the exponential function with a power x plus y over x minus 1. Okay, so if you're gonna integrate this function using dx dy, right, you know how to do it or not? E to the some power, some complicated. Can do or not? You think you can do it? Cannot. Okay, so turns out that if you use transformation of variables, then you can do it easier. So what's the integration domain here? This integration domain is this trapezoidal region, trapezoidal region here, so bounded by four axes, 1, 0, 2, 0, 0, -2, 0, -1. So what's the diagram here? So actually, this diagram is the diagram below here. Okay, that makes sense? Okay. All right. So, what's the sensible transformation you can do here? Well, uh, since this is a function of two variables, so if you're gonna do transformation, right? Obviously, you want to transform to the other two new variables here. Okay. So, well, there are natural choice here. Okay, 自然的选择。In mathematics, there are a lot of things is natural. Yeah, there are a lot of things natural. Meaning, the question itself will point to you what to do. Okay, in this case, you can see that there are clearly one portion here. Right? There's numerator here, denominator here, depending on x, y. So why not just let the numerator as a new variable and then the denominator as a new variable? Okay, maybe there are other ways, but this is one of the way, right? We could try this way first. So if you let u equals to x, v equals to x minus y, then what? Then you can find what's the transformation you make here. So you really have a one-to-one transformation from where to where? From u to x, v to y, where x equals to u plus v over 2, and then y equals to u minus v over 2. Okay, now, so under this transformation here, you can see that how your domain get changed. Okay, you can see that how your domain get changed. So like what we did last time, right? We first determine how these boundary set get transformed first. Okay, so if you make a calculation on these straight line and what and linear line here, okay, and then you will see that it get transformed to the other trapezoidal region. So remember last time how we discussed how we transform the point inside the boundary. Okay, inside R, how does it get transformed here? How do you check it? Remember how we discussed about this point here? One way to discuss it, you can imagine that these boundary points are spanned by these straight line. Okay, and then you can look at the image of this straight line here. Okay, so let me draw something here. So if you split up your region using these linear line with different gradient, under the transformation, you should compute that they also get sent into the horizontal line in the new region. I call it X here. Okay or not? And you can compute infinite family of them because the difference between these lines is just the gradient. The gradient or not? You know how to get this line? So you can see that. What can you see? These R4, I call it R4 here. What's this line? Y equals to minus x minus 1. How about the other line? Y equals to minus x minus 2. So the difference is not gradient. Or the difference is just the, what? You consider all these purple line. Is the y-intercept. Okay, so the y-intercept span between where and where? -1 to -2. So you can see that they all get sent to the horizontal line in between the new part. Which line is this? This is a new R4. This one is a new R2 here. Okay, remember one thing is once you do the transformation of variable, what's the extra factor you have in your integral? Now with a Jacobian. Okay, so you need to compute the Jacobian. What's the Jacobian? It's the determinant of all the partial derivative. Okay, all the partial derivative. And remember, when you take Jacobian, right, you need to take the absolute value of the Jacobian because we don't want the sign from the Jacobian to affect your integral. Okay, so then you do the actual integration. Okay or not? Any question about this change of variable here? Okay, a few things you need to remember when you do this calculation is one of them is the change of your domain, integration domain, and then the other is the Jacobian. Okay, other than that, you just do the normal integration. That's all. Okay, no? Okay. Obviously, when you do this transformation, you need to be one-to-one. But in this course, usually it's one-to-one. Yeah. Well, I mean, do you know how to check one-to-one or not? Do you know how to check one-to-one? Can you write this T into a matrix form? Can you write this T into a matrix form? In this case here. If you are given this two equation here, can you write the matrix form? Can you figure out the matrix that you multiply to UV such that you get XY? How? What do you get? What's the matrix you get? Huh? Huh? Over 2? Everywhere? Where's the minus 1 over 2? The last one? Okay. So if you want to show that this map is injective, it's equivalent to show that the determinant here is non-zero because it's invertible. Invertible means what? Is surjective and injective. But you need injective only. Can straight away see this this matrix is invertible matrix or not? How to check out? How to check a matrix is invertible? Yeah, the domain is non-zero 0. Actually, you are computing the determinant already, right? That is what? That's your Jacobian. Okay. Yeah. Okay. Now, if your Jacobian is 0, what happened? Huh? Cannot transform. But if you really put into the integral, then what happened? 0. Everything is 0. Okay. Compute everything to be 0. Okay, so that's why we want the Jacobian to be non-zero. Okay, no? Yeah. Okay, so this is it. So quickly summarize what we have did for the multiple integral. So first, we define the double integral as what? As the doubly limit of doubly sum. So what is doubly limit and doubly sum? The doubly sum here is the volume. Okay. Why we take limit? Because we try to make the cuboid volume of the cuboid smaller and smaller such that you can approximate the volume under the surface better. Okay. Until it reach a single line. Remember, we reduce the size of the cuboid. And then, well, we cannot use this definition to compute in our course. So what do we do? So we introduce a bunch of tools. First tool is if your surface is always positive, right, or non-negative, then how do you compute this double integral here? You just compute the volume under the surface if you know it. If the volume under the first surface is a box, then you just use volume of box. If the volume under the surface is a sphere, then you just use sphere formula to compute it, and so on. Okay. Then, what do? We introduce the property of multiple integral here. So your multiple integral is linear. So meaning what? If you have a domain, okay, which is a union of two sets, but their intersection is just on the boundary, then you can split your sum into the integral on two sets here. You cannot. This doesn't apply if the intersection of these two sets has some cannot set non-empty. So how should I put it? The intersection here is that has a non section non-zero integral. Okay, I'll say that you cannot, if you intersect more than a boundary, you can't really apply this definition. In later course, you will learn something called measure theory. And then if you do measure theory, right, this boundary line here, we will call it a measure zero set. Okay, because the integral on these intersection is zero. This boundary here is zero. But if you intersect more than the boundary, the intersection around here could be non-zero. If this intersection here is non-zero, what can you imagine? If you split them, you will compute this non-zero integral twice. It's like the set theory, right? When you do what? A intercept B. So when you do these things, right? So similar to an idea of set theory. So what's the formula of A intercept B? A union B. Hey, sorry. What should I say here? What's the thing I want to say here? What am I trying to say here? What's the thing that's equal to A union B that take away A intersect B? What's the thing I'm trying to say here? Cardinality. Did you guys learn this? Cardinality of A union B is the cardinality of A plus the cardinality of B take away intercept B. You learn this? Yeah. Okay, so this is a similar idea here. So if you compute A union B, you obviously you can add the number of elements from A and the number of elements from B, but if they have non-trivial intersection here, you are counting the intersection twice. Okay, so similar idea. Similar idea because counting and integral is really similar. Because counting is just a discrete way to add things up, but integral is a continuous way to add things up. Yeah. So similar idea. Okay. Next, area of the domain. So in principle, volume under a surface is computed under using double integral. But if you integrate over function constant function one, really what you do is you just compute the area of D, okay, or area of your domain. Because what? Because the area of your domain is equal to the volume of your domain with height 1. Remember? Height 1. So a cross-sectional area of your box is the same as the volume of that box with height 1. Okay, because area times height is your volume. So if you integrate over a constant function 1, 1 is your height. Next is an order preserving property here. So if your fxy is bounded by two constant functions here, then your double integral of that will also bounded by 2 volume here. Okay, what's the 2 volume here? Is the area of the domain multiplied by the height little m and pm. This is not always true for any mathematical objects we define. Or sometimes some of the mathematical objects, right, will reverse this order. Okay, so this is not true always. But for integral, it is true. It will preserve it. Some mathematical structure will reverse it. Some mathematical structure. Or some mathematical structure just don't preserve this kind of order. Okay, so integral is kind of a nice thing because it will preserve order. Okay, and then we learn Fubini's. Okay, the other way to do integration is Fubini's. So Fubini's start with what? A continuous function on rectangle. You just know how to integrate on rectangle. So why is the rectangle good? Because all your variables are bounded by constant number. Okay, and then it doesn't matter which integration you do first. Okay, you can change. You can do dx dy or you can do dy dx. And if you do it for polar coordinate, you can do dr d theta or d theta dr. Okay, and then from Fubini's theorem on a rectangular region, we can generalize it to general region. Okay, such that we can bound this general region using a rectangle. Okay, and then we can and then we can still apply the Fubini's theorem. Next, we look at different coordinates. So we integrate over different coordinates. For example, in R2, we can go from a rectangular coordinate to polar coordinate. How do we do this change of variable? This is exactly the same what we did in the previous chapter. Okay, so we use x equals to r cos theta and then y equals to r sin theta. The most important thing here is to mind you that there's a Jacobian factor. Okay, when you do change of variable. And then why one is favor over the others? Okay, why one is favor over the others? This really depends on the integration domain you have. Okay, if you just integrate over some rectangle, maybe triangle, some very, how to say, it's a variant of trapezoid. Okay, then you would use a rectangular coordinate. But if you're gonna integrate over circle, okay, or annulus, or half annulus, then polar coordinate will be favored here. Because remember what we did last time, why polar coordinate is favored over a rectangular coordinate. For example, circle. We cannot describe a circle using a function in x1, but if you just look at the polar coordinate, I can see circle as a function. How to see a circle as a function? Actually, circle is a constant function in polar coordinate. Right? You just set your radius to be some real number. That real number is the radius of your circle. It's a constant function. Okay, so polar coordinates make some function become easy. Okay, okay, so when you do this change of variable, be mindful about your what? The range of variable that you use. Okay. So in xy, you will cover everywhere from negative infinity to infinity here. Can I write equal? Seems like not good. I don't think we can use this. Don't use equal here. Okay, and then on the other side, how to cover an R2? You need radius from 0 to infinity, and you just need angle from 0 from 2 pi. Then you can cover everything in pi. So another advantage of using polar coordinate, can you see or not? If you are using polar coordinate, right, 3 of the bound is finite actually. Okay, 3 of the bound is finite. Okay, now can you see? 3 of the bound here is finite. Okay, but in SY, you really need everything inside your real number. But here, you just need 0 to 2 pi for theta, and then radius just start from positive 1. Then you can cover everything. Okay, so this is another advantage to use polar coordinate. And in R3, we have a analogous thing here. So we can go from rectangular to spherical. We also can go from rectangular to cylindrical. And then I write out the transformation in between them. And right, so similarly, you should see that what object is favored, what integration domain is favored under each coordinate. Then when you are given a question, you draw the domain and then you see that, oh, this one looks like a cylinder, then you will consider cylinder. If this one is just a box, a random box, then you just use the normal rectangle. Or if you see the integration domain is like a sphere, then you just use spherical. Another reason why you want to swap coordinate is maybe your function itself. Okay, your function itself is stated favorably over spherical coordinate or cylindrical coordinate. Then you will change it. Okay, and after you change it, like what you did in the starting examples, right? Your integration domain will also change. Okay, like just now, your trapezoidal region will change to the other trapezoidal region. So maybe if you do the change of variable, your integration domain also change. And one more thing is to remember is the Jacobian factor here. Okay, please remember the Jacobian factor here. Actually, in this case here, there are not many Jacobian factor to memorize, right? You should remember that the cylindrical coordinate is just one more variable than the polar coordinate. So it is using exactly the same Jacobian thing because Z is just Z. Okay. And one more new thing is about this spherical here. It is r squared sine phi. Okay, that's all. So basically, it's just r and r squared sine phi. Okay. For the other transformation, you need to compute yourself. Therefore, these two are kind of fixed. Okay. So you can see that spherical here, out of 6 bound here, 5 of them are finite. Okay, out of 6 bound here, 5 of them are finite. And cylindrical, how many bound are finite? 3 of them. Okay, it's really similar to the polar one. Okay, now, any question about this chapter here? Any questions so far? Okay, so if no question, please try the after chapter exercise, right? I have posted out. Like every chapter finish, there's a set of question you can try, and you should try the tutorial one. This is a Jacobian. Okay, so before we go to the next chapter, we want to review a bit what we have did so far. So where do we started? So we started with a sequence and a series. So these objects are coming from function from n to r, and also function from r to r, like the power series. And then after that, where do we go? We go to parametric curves. Okay, parametric curves. So what do we do with parametric curves? What kind of object we work with? Function from R to R2 or function from R to R3. So these concerning about how we see lines in R2 space, how we see lines in R3. So these are very natural. Right or not? How many of you drive here? How many of you drive? You all. So when you drive, right? When you drive on the road, you typically will path out a path in R3. Okay, so this is a function from R to R3. And next part is what? Next part is about multiple integral, multiple derivative, partial derivative. Partial derivative. So, well, I mean, partial derivative and multiple integral uses the same objects. So what sort of object we see here? These are functions from R2 to R or R3 to R. Okay. So R2 to R, R3 to R, how to think about this function here? You should think about this function as you have a R2 or R3. This R here will tell you the height of this point. Okay. So this R will attach a number to these points in the domain. Well, I mean, you might think that there's a different way I describe this function. You should also be able to use the language I use here to describe function from R to R2. Meaning what? For every point in R, you can attach a vector in R2 and R3. But what does this mean actually? What does this mean? So there's one connection you need to make always. Okay, how to make connection about R, a vector in a plane with the coordinate. Okay. Do you realize that whenever I give you an xy vector in R2, for example, this is just a coordinate on R2. Where's this coordinate? This is coordinate such that the x coordinate is x and y coordinate is y. Okay, so this is very natural identification here. So whenever I give you a vector in R2, you should imagine it is a point there on R2. So if you say that whenever I give you a number in R, you are attached to a point, meaning what? And this function is continuous, okay, meaning when R changes, R square also changes. So the natural thing to think about it is you think of this R as a time, because time is kind of continuous, right? Okay, I cannot say time is continuous. Then later, I have a student saying variable is continuous, so better don't do this. So I would say that a flow of time is continuous. Okay, the flow of time is continuous. So when this R changes, okay, your position in R2 also changes. If this changes is continuous, then it will path out a continuous path. Okay, so any question? So you have seen quite a lot of mathematics object or function here. So next up, we'll learn about vector function. So what's about vector function? Let me see first. Let me see, yeah. Okay, I think we were kind of a little bit going backward to this parametric curves here. Okay, so vector function is about this part here. Okay, last time you see this function as how time changes in spaces, but this time around, I want you to see it as a vector attached to a time. Vector attached to a time. So your core domain is a vector. So give you a time, then you can give any point in R. Okay, your output is a vector. But if you look at this, the third part here, the output is just a number. Actually, this number is also regarded as a vector, but we'll see a higher dimensional now. So for this chapter, right, you don't need to be too worried about it. It's just to recall some knowledge, or just just recall some knowledge, and then this knowledge will be used in the next chapter. Okay, this chapter won't be tested, but we will use this language in the next chapter. Okay, so I will quickly run through this. Well, so what's a vector function here? So we try to relate it back to the space curve we learned in parametric curve chapter here. So it's a function actually from R to R3, okay, or R to R2. So how to describe a function from R to R3? In R3, you need to give me a vector. So this vector, how to write this vector? This vector has three variables. So to give a function is just equivalent to say that how these three variables depend on the one variable you give the domain. So you need to write three variable as a function of t. So we have three of them here: ft, gt, and ht, for example. Okay. So there are a few ways to write it off. I already introduced these three ways, right? You can write it as a row vector or column vector, or using the IJK notation. Okay, it's the same. 有问题吗？啊，有问题吗？没有，有问题可以问。没问题啊，OK。因为我看到你很沉重，想问一下你有什么心事，要不要说说看？OK。So I'll run through pretty fast. If you have a question, please stop me. Because I assume that I said pretty clear. So if you think that I'm not clear, you should stop me. Because I'm different from the other lecturer. The other lecturer maybe they taught in class that they don't want you to listen. They ask you to go back and read. Someone asked the other lecturer, 老师你讲这样快，我们跟不上。然后你知道那个老师回什么吗？我的速度没有一个学生可以跟得上。So just stop me, okay? If you think that I'm not clear or what, okay? Maybe it's not your problem, okay? It's my problem, so you should ask me, and then I will repeat for you. Okay. Okay. So next part, given this vector function here, okay, so written in three function here, try and find the domain. So this is similar to what we did last time, right? Find the natural domain, okay, where these the domain makes sense. If you look at this three function here, t cubed ln 3 minus t square root t, which function has a restriction on domain? 来，慢1秒，2秒，3秒，没有了，给他。Which one has restriction on domain? Ln and square root, right? So for square root, what do you need to satisfy? Everything inside must be of non-negative, you could include 0, right? Okay, so you need to make sure your t is greater than or equal to 0. Ln also the same, right? Ln is more restrictive. Your thing inside have to be strictly greater than 0. Okay, so 3 minus t have to be less than. T has to be strictly less than. So if you combine these two conditions here, you will get t less than 3 and greater or equal to 0. Okay. So meaning what? This space curve here only works for time from 0 until somewhere before 3. And somewhere before 3. Cannot reach 3, but anywhere before 3. So this is what is defined to be a vector value function here, okay, of a variable t. So we associate a real variable t with a vector rt. Yeah, 往上一点，怎么样？ OK， 好。OK， right. So I said that I will sketch one of the example. So let's see. Let's try and sketch this example. You can try and sketch the previous example, but we will sketch this example. So in the coordinate t, in the coordinate x, how does x move like a quadratic function? But in the y direction, how it moves? It moves like an exponential function. So you should imagine that in the y direction, it should move faster than the x direction. But in the z direction, it just moves as a constant speed 2. It's a constant speed 2. It's not constant speed 2, but constant speed 0 at the coordinate 2. So how it works, let's see. Well, one very easy thing to do is you plot out a few points first. Okay, you plot out a few points first. So for example, for me, right, what do? I try to plot out what is R0, R1, R2, and R minus 1. And then I try to plot it in R3. In this case, it's R3. It's R from R to R3. So where is my negative 1 point? Let's see. Wait, let me sorry, let me combine for you. So here is the t0 time. Where's the t is equal 1? T equals 1 times is here. Equals 2 times here. Minus 2 is this one. And t equals minus 1 is this. Okay, so you can see that there's an orientation on your curve here. Okay, so you can see that I put a lot of negative, not negative, cross here, cross there. You know why I put a cross there? What do I mean by I put a cross there? You cannot see the color carefully. Maybe I change this. Okay, so well, I mean, why I put this cross there is because if you look at this quadratic function, right, the range of this quadratic function is always greater or equal to 0. So meaning for the x coordinate, for the x coordinate, right, you will never reach the negative x. So that's why I put a cross at the negative x region. And then if you look at the range of your y, this is a exponential function. Exponential function means what? It is always positive also. So you won't reach the negative y region. So that's why I put a cross at the negative y region. So your curve should lie on this side. Get the side that's facing you. So when you plot it out, yeah, true. It is living on the side that close to you. But what? What's the plane it live on? Can you determine what's the plane it live on here? Z equals to 2. Actually, this is not the origin. 不要被我的那个三个 intersection 骗掉啊。I put a 002 there. Okay, so actually it's on the plane of Z equals 2. It lives on the plane, right? Why? Because on the Z coordinate it is constant. OK， 它一直活在那个高度，就是你在第3楼，比如说你在第2楼，你就在第2楼走动嘛。OK， 你没有去到第3楼，你没有去到第1楼，你就在第2楼。Because your Z coordinate is always the same, always the same. OK. OK 呢 ？Any question？ 有问题吗 ？I think it's pretty clear. If you are not clear, please ask now. OK， 有问题吗 ？Yeah. Okay, next part is about after we introduce function, right? We will talk about limits. Okay, it's the same here. So how do you take limits of this vector function here? Based on your intuition, you should take limits on every function. Because why? Every function is just a function from where to where. These three functions is from where to where? GT, HT, RT. What's the domain and codomain? Whenever you talk about function, you must know domain and codomain. Otherwise, you are bullshit only. Okay? So you must know what's the domain of FT, what's the codomain of FT, and GT and HT. What are their domain codomain? R to R. Okay. So you know how to take limits for function, one variable function, right? Okay, so now we just taking 3 times limit. Okay, taking 3 times. So how to take a limit of a vector function? You just take limit at each uh, uh, each uh, each coordinate. Okay, function each coordinate. And then similarly, if you want to have continuity on your vector function, you just check that this separate limit here will converge to where? Converge to the point where you evaluate your vector function at A. Okay, the point you're interested in. Okay, it's the same. Okay, so you just need to check in 3 separate coordinates. So for example, this case here, okay, let's quickly go through one example. So if we want to compute the limit, okay, of this vector function where t goes to 0, how do you compute it? You just compute it 3 times. Okay, compute at every coordinate here. Okay, you just compute it every coordinate. If you compute it in every coordinate, right, this is just something in calculus 1. Okay, so so last time we have talked about this space curve idea, right? And then about the parametric curve. So how should you think about it? So given a time t, the the vector here tells you the position in R3. Okay, and then if you connect them together, it is a curve. Okay, so let's give some example, real examples here. Let's give some real examples here. So let's go through these basic uh, curve. So for example here, describe the curve defined by the vector function here. 1 plus t, 2 plus 5t, and minus 1 plus 6t here. So if you write it in a column vector form, I think it's more familiar to you, right? Do you see this kind of combination before? A vector plus a vector and a variable. Huh? Some solution to a null space, right? You sometimes you get this kind of a combination. Vector plus a vector times t. Right? So usually your null space is a line. So this is a line. Why is it a line? How to see this as a line? So to see this is as a line, right? You should remember these general formula here. Line is equals to a vector is equals to a vector plus vector times t. So how to define a line? How to define a line? If you want to talk about a line, how to describe a line actually? How to describe a line? And go back to a basic question. How to describe a line? I mean, if in high school, right, how your teacher teach in high school, you get 2 points on your line, and then okay, let me use another bigger. So if you want to get a line, what do you do? In high school, you get 2 points, and then what do you compute? Yes, good. So basically, y1 minus y2 minus y1 over x2 minus x1 equals to y minus y1 over x minus x1. Ever wonder where this formula come from? If you rearrange these formula here, what do you get? You get this right. And then in the end, you will get that the line of equation is y equals to okay, so there's a y-intercept here. And what you started with actually is the gradient. Okay, but we can write this in a vector form. Okay, we can write this in a vector form here. So what's the vector form here? So the vector form here is, instead of getting 2 points on this line, we simply just get the vector. Okay, we just get this vector is enough. And then this vector will spam out a time. Okay, so what's this vector here? Can we relate these two together? Can relate these two together. So what's this vector here? How to get this vector? Well, I mean, let's make life easier. Let's start this line at the origin. Okay, let's start this line in the origin. Okay, and what's this vector here? You can see that this function, this line is spanned by this vector y2 and x2, x2, y2, right? This way. Okay. And how to get different points on this y2, x2 here? You just multiply by time t. So meaning what? You are scaling this vector here. Okay, you are scaling this vector here. Okay, you are scaling this vector here. But there's a lot of line with this vector here. For example, I can draw a parallel line, okay, with the same direction here. But how to determine which line is which? Okay, how to determine which line is which? Okay, how to determine which line is which? Determine which line is which. So, for example, these three lines have the same direction, right? Okay, these three lines have the same direction. But how you differentiate these three lines? Sorry? Huh? Cancel V0, what does it mean? A line equals what? At least? Uh-huh. Then? Depend on the V0. What does it mean by depending on the V0? Can you see that these three lines is also different now? What's the difference between these three lines? Okay, 1%, not just 1%, right? Every point on these lines are different actually. Fair enough. If all the point is the same, why not? I mean, they should be the same line. Why I can draw three different lines here? So I when I put x squared x2 y2 times t, that's just a direction with time t. But this function here will realize the point on your line. Will realize the points on your line. Should I give you a how about let's give an exact example here, otherwise cannot see. So let's give an exact examples here. So let's take 1 here. So maybe this line is 1 times t. And then the other line maybe is a 2. There's one of them is this one is 0.5, 0.5. Okay, so if you're gonna make the equation for, let's say this is line 1, okay, line 1 here should contains 1 here. Okay, line 1 here should contain. If it contains 1 then basically you are done. Let me think. Am I right? Huh? Sorry? Huh? Which one? Oh, 2 is also what I want. So I think I make some mistake, right? So maybe make this into 1, 2, and then this one make it into This one 1 or 0, like that. Okay. Yeah, basically, if your line contain 1, then you are done. If you can realize this point here. Okay. So what I want to say is, if you want to make a line, what do you need? You just need a point and a direction. Okay, you really just need a point and a direction. Then you can make a line. Okay, so this is the definition of a line. Okay, so a line is just one dot with a direction. Okay, yeah. No question. So this is similar to the plane. No? For the plane, you also just need a point with a direction. But what's the direction you need for a plane? The normal vector. Okay. So there are few ways to map planes. Oh. Okay. So let's quickly go through this and then we can take a break. So for a line, how do you make a line? Either you tell me 2 points and then you join it. Okay, this is what we learned in high school. Or you also can take a point with a direction and then you can make a line. Okay, so these are the two ways to make lines. How about plane? Okay, how about plane? So plane, there are a few ways also. You can take two vector living on the plane, and then from this two vector here, you can take a cross product such that you get a normal vector. And then from here, you also can make a plane. Or simply, you just take uh, a point on a plane and then a normal vector. You will spam out a plane. So here is two vectors, two say two linearly independent vectors plane, or um, 1 point and a normal vector, 1 point on plane and a normal vector to the plane. Okay. So the other case, what do we have? 2 points on line, or you have 1 point with direction vector. Okay, so these are the ways that you can make line equation. Okay. Yeah. Okay. So let's take a break until 10:10. We'll continue with examples of space code. Okay, before we start, so starting from this weekend, you can start sending in the project to topic to me. Yeah, you can start sending in to me. And then next week, if you have draft, you can start sending in to me. If no draft, also never mind. You can straight present, and then we will find your mistake on the spot. Then you will try and adjust in your project before submitting. Yeah. So your thing is meant to be question, because you cannot say that, oh, 我做了这事情，我觉得我对我就对. It's not like that. Because even for our paper, if you submit outside, the editor still will ask one, 这个是什么意思？这个 line 是不是错了？这边 we will do editing few times, okay, before it get published. So it's the same. Okay, 不是你做的东西就一定对的，你以为对的东西你就一定对，不对的。Okay, you have to convince the others. Okay, you need to learn to convince the others. Okay, no. Yeah. Okay, so this is the thing you need to learn. Okay, throughout this course, how to talk to the others properly. Okay, talk to the others properly. Okay, so for this one here, so let's look at this space curve here. So the first coordinate is cos t, second coordinate is sin t, third coordinate is t. So you can see that the first and second coordinate, right, will satisfy what kind of equation? Cos t and sin t. Huh? Cos t and sin t will satisfy what equation? Trigo equation, for example. Huh? Cos t and sin t will what trigo equation satisfy? Huh? Cos square plus sin square equals to 1. So meaning what? Meaning this x and y coordinate will stay on the circle. But now this point in the circle, every point in this circle, right, being attached with a height t. So meaning what? When t increases, the circle on the point also increase. Okay. So you can see that if you start your curve at 1, 1, 1, 0, 0, what happened? The point on the circles, right, on the xy plane gets spiral up. Okay, when the time increases, the height of the point also increase. But since they are connected before, right, so it should be connected also after increasing. So you can see a spiral up curve here. Okay, spiral up where? Spiral around the cylinder. Correct? Around the cylinder with the radius 1. Okay? Does it make sense? Any question? Anything you don't understand? See? Okay. So in general, you can go and use a GeoGebra to check it. Okay, next. This is about finding a vector equation and parametric equation for a line segment. So previously we found a line, right? So what's the equation we're talking about? So there are two ways to describe this line. So one way is using this L equals to V0 plus Vt here. So why I put P here? So you could see the vector V0, right, as a point on your line. Okay, it's a line with your direction vector times t. Or you can write it as a parametric equation here. So what's the difference between these two? What's the difference between parametric equation and line vector equation here? Ah, yeah. So what's the difference? That's why I asked you. What about x, y, z? Then that then. Yeah. Almost the sense or not exactly the same, right? So must be a different. So what's the difference? vector equation, parametric equation 什么差别 It's the same, exactly the same, but parametric equation here stop every variable. I just list every as variable out. Vector equation then I write them as a vector form. Okay. Okay, so what's the L here? L is the vector that have x, y, z. Okay, so parametric equation here just split all the x, y, z out. That's all. Okay. OK 了，有问题吗？看得到吗？慧琪，那两个东西是一样的，为什么一样啊？为什么不一样？为什么一样？为什么不一样？OK，还有呢？啊，good good，好，非常好，Yeah，一个放在一起写，一个分开写，good，Yeah。One is a vector form, one is in terms of variable. Good. Okay, so for this point here, if you don't specify t, the line equation or the parametric equation will span whole t. But this question just asks about a line segment joining these 2 points here. So you should cut your line at the appropriate t. Okay, you should cut your time at the appropriate t. In this case here, with the right choice, because we start with the point where we started, and ended with the point of this direction vector here. So we just pick our time from 0 to 1. And then how do you check? How do you check where you cut the right time or not? So meaning at the starting point, you should start with P. At the ending point, you should start with Q. And in this case here, does the direction matters? Does the direction matters or not? Direction matters or not? Direction of the line matters or not? This line comes with a direction, right? So from P to Q. Can I draw a line from Q to P or not? Can or not? Huh? Can. Why? Because this is just asking a line segment that join the two. It doesn't say that have to start where. If it says that you have to start at P or start at Q, then you need to make sure that the starting point is the right one. In this case, only it's just a line segment that joins two. Okay. Unless the question asks about line segment that start where, then the orientation become very important. Okay, no? You know how to change orientation given this line equation here. You know how to change orientation? How to change orientation? You just make your direction vector negative. Okay, so you will go the other direction. Okay, no? Correct? What is 1, 0, 0? Going to the right, right? If negative 1, 0, 0, then going to the left. Okay. Okay, next, try and find a vector function that represents the curve, intersect the cylinder, and the plane. So you get these cylinders and plane here. So if you get this intersection, you will draw a ellipse. Okay, you draw an ellipse. 哎，这个就是我上次要跟你讨论的那个 frisbee 的东西。Yeah, okay. If you take a cylinder and a plane, you will intersect out an ellipse. But how do you write down the vector function? So do you reckon that you can use a vector function to describe this curve here? Because given a time t, you can give me a 3D point. Okay, R3 point inside R3. So how do you do it? Okay. So first of all, what does it mean by line in the intersection? To line the intersection means what? The x, y, z coordinate have to satisfy both equations. Okay, so to satisfy both equations, you could start with one of them. Okay, for example, how I start. So first of all, to lie on this cylinder here, right? Your x and y coordinate have to satisfy this square equation. Sorry, this trigo. Right. Yeah. But you need to satisfy the other plane equation here. But the plane equation here, the z will dependent on y. So if you fix your x and y, pretty much your y is fixed already, then your z will be dependent on your y here. Okay, so in this case, if you put all these variables together, the vector function that you're looking for is cos t sine t 2 minus sine t. Okay, so maybe this is the crispy trajectory you mean. Something like this, something like this. Okay, something like this. Okay or not? Yeah. Okay. Yeah. Any question so far? Question so far? Okay, let's continue. So next one, similar things. You want to look at you want to find a parametric equation for a curve of intersection between paraboloid and a plane x equals to y equals to minus x. So what do you do? Well, what do you do? So you need to figure out the curve of intersection first, right? Okay, so you figure out what's the curve of intersection here. So if you let y equals to x, okay, and then you substitute into your paraboloid, what do you see? Actually, you see a circle. Okay, actually, you see a circle there. So how to describe a circle here? How to describe a circle here? So you let x minus 2 equals to 2 times cos t. Why there's an extra 2 here? Just now there's no extra 2 there, right? No extra 3 there. So why is there an extra 2 here? Because the circle here is no longer radius 1. Okay, so this radius is 2. And you have z equals to 2 sine t. But to find out this vector function here, right, you not only need x, you not only need z, you also need y. So how to find y here? So you should see that y is dependent on x. So y is the same as x. Okay. So in total, what do you get? You get this parametric equation. So what does it mean here? What does it mean here? So it's a shifted circle in xz plane. Can I say xz plane here? Yeah, xz plane, but it is lifted on y direction. Okay, it's lifted on y direction. So you should imagine, how do you imagine this circle here? So if you just look at the xz direction, so it is a circle like this, okay? But every point on the circle get attached with a different y. Okay, every point on the circle get attached with a different y. So this circle is kind of get maybe enlarged a bit. Yeah, get enlarged. Can you imagine what I'm trying to draw here? So if you just look at the xz direction here, so this is a shifted circle, right, with radius 2. Okay, but with the extra y coordinate here, every point on this circle, right, get attached with a different y. Okay, yeah. So it becomes like an enlarged circle. Imagine. Okay, yeah. How you control this y? This y exactly follow how x grow. Here's the same growth. Okay. Okay, let's continue. Okay, this example here was tried by my previous student in AIT. They pick it from the tutorial, from the textbook. I think it's one of the questions in the textbook. X equals to t cos t, y equals to t, and then z equals to t sine t here. Well, I mean, if I give this question to you, how should you imagine about this question here? There's cos t sine t here, right? Okay, so this is x and z kind of satisfy what equation? Whenever you see cos t sine t, right, you should try and square it. So this equation satisfy what? T square sine square t plus t square cos square t equals to. Okay, so there are some circle involving, but the t is keep changing. So depend on your t. Okay, t square, but t after t square becomes what? Radius is positive. Okay, so when t get larger, this radius will get larger. So you should imagine the circle like keep growing large when t grows, okay, from both sides. But y, what happened to y? Y is just a normal moving y equals to t. When t move, y just move as a t. So how should we imagine this shape here? So I kind of feel very interested, so I draw it up and then I include this here. So actually this is a spiraling along y-axis. But this is very interesting. The way it spiral when t is negative and when t is positive is different. So if you follow one way, okay, so if you follow the negative t spiraling inside, you can think of it as a counterclockwise, right? Okay, but after t positive, it becomes clockwise. Okay. So negative t and positive t is different. So you can see that when the scalar get smaller or larger, right, the radius get larger. Okay, but spiral in a circular form. Okay. Yeah. Another thing I thought about this shape is if you pass by some temple, do you see this kind of thing? Maybe half of it, finite of them. 有看过吗？有人点那个香啊，还这样烧上去，烧上去，烧上去，烧上去，烧上去。You know? If you go to a temple, you see this. 有看过吗？没有看过啊，建彤。还有要给建彤看一看，是不是吗？对，香，有看过吗？中国看过吗？中国有看过吗？看一下我找不找得到啊？我那天应该要拍起来，但是我找一下。呀，这个我觉得这个够了。哎，这个你去庙里看一下这个东西。OK。Yeah. You can ask the question why they design like that. 不懂，我不懂。去庙里面问。Yeah. Is it aesthetic? Is it aesthetic or 还是有实际用途？它方便取啊，方便收纳，或者它可以。还有可能一个更可能的事情，就是它可能烧比较长。你看，如果这个香啊，就这么短吧。假设你要烧这么长的香呢，怎么可能插这么长呢？对不对？那它就卷起来了。也有可能也有其他寓意在啊，可能有宗教的原因在。But yeah, practically 来说，yeah, 可以讨论啊。其实这些东西是可以在你们的 project 讨论，还可以把宗教带出来。OK， yeah. So Max is really live. People live in life use Max, although they don't realize it, but it is Max. Okay, let's continue. Okay, continue. After limit, after continuity, obviously what we need to do, derivative and integration. So we can do the similar thing to vector function here, but you should realize one thing here. You should realize one thing here. When we consider the limit here, right, this RT plus H and RT is a vector already. Okay, it's a vector. Difference between vector is different from what we did before. Whatever we did before or your calculus one is just a difference between two numbers. But here is difference within vectors. Okay, and then you divide vectors by a h, a scalar, and then you take limit. So you take limit on vectors. So just now I told you how to take limits on vectors, right? You just take limits at every spot, and every coordinate. Okay. So you can see that when we see the small changes here, right, it is really difference between two vectors here. Okay. Previously, it's just the difference between two value, two numbers. But here is vector. Can you see or not? Vector. So you see the difference here is another vector. Okay, difference of two vector is still a vector. So it becomes this vector here. Okay, previously it's just but but we still don't really care. We will straight away tell you how to differentiate differentiable functions such if every spot is differentiable. Okay. One thing is one thing about tangent vector is this unit tangent vector here. So if you compute the derivative of your RT, then sometimes we will want unique tangent vector. Okay, this is very important when we do integral in vector calculus later. Okay, unique tangent vector. So we normally just care about tangent vector with length 1. Okay, so meaning what? Meaning you need to differentiate your vector function first and then divided by its length. Okay, and how to differentiate? So next part tells you how to differentiate. Typically, what example you see will you see was all the coordinate vector will be differentiable. So what do you do in that case? You just differentiate all of them one by one. Okay, just differentiate one by one. Can differentiate one by one now because this is just a one variable function. So you can do the usual derivative. Okay. Yeah. So for example here, let's give a quick example here. If we start with a vector function here, how do you differentiate? You notice that everything inside is just polynomial or exponential function. So you can simply do differentiation. Okay, so you differentiate one by one. Okay. So I think so far it's okay. Okay, so what's the use of the tangent vector? So what's the use of the tangent vector? So the tangent vector that you find for a vector function, right, is actually the direction vector to your tangent line. Okay, so let me underline this. Okay, so this is the tangent vector. Okay, so the tangent vector is a direction vector for your tangent line. Okay, so to give you a context here, so let's say I have a RT. Okay, maybe just use this example to describe. So if you look at a parametric equation for this helix here, so what's this helix here? This helix, you see, is a distorted circle here. Okay, they don't add up, but they kind of add up. Okay, so an increase in t. Okay, so you can see that it's spiral like this. Okay, kind of like a circle, but not quite, because their scalar is a bit different. Okay, you can't quite get the radius properly. So this asks you about a tangent line at 0.01 pi over 2. So it's this point here. So let's put it up. So how do you do this? So first of all, you just get the tangent vector. Okay, so after you get the tangent vector, then you use this tangent vector to build your line. Okay. So tangent vector just give you a direction vector, but you need a tangent line. Lines, what's the ingredient you need for line? A direction vector and a point. Okay, so what's the natural point to look at here? Huh? What's the natural point to look at here? What's the natural point to look at? Intersection point or the point that you're interested in. Okay, so the point you're interested in here is what? 0, 1, and power 2. Okay, so you should use that point and the tangent vector to build your line. So what do? So to get a tangent vector, you just differentiate your vector function. Okay, so to differentiate vector function, you just differentiate term by terms. Okay, term by terms. And then after that, this is your vector function, and then you should get your point out. But not that this vector function here, this tangent vector here is a function. Can you recognize that this tangent vector is a function? Okay, so this is a function in t. Okay, so this is a function in t. So how do you get the exact direction vector on that point? You simply evaluate this tangent vector at the time that you are interested in. So where's the time you're interested in? Can you figure out from this point here, where's the time you're interested in? Power 2. How do you get power 2? Because the z coordinate exactly tells you what time you are at. Okay, so you just put power 2 inside your tangent vector function here, then you get the exact vector. Okay, so the parametric equation for your line is simply x equals to minus 2t, y equals to 1, and z equals to power 2 plus t. Okay, no? So now we try to put a lot of ideas together now. Okay, how to find lines, how to differentiate, okay, and then put these ideas together. Okay. Okay, there are certain differentiation rules here, a bit different from what we learned before, because you need to remember that now we are differentiating over a vector value function, okay, not scalar value function anymore. So what are the same? So for example, number 1, number 2 is the same. Okay, so derivative act linearly on this function. So you can pull scalar out or you can split the differentiation. But in number 3, what happened here? What if you consider a product of a function, okay, a scalar function with ut? Okay, so what's the difference between ft and ut here? ft, the codomain is just a scalar. So do you have product rules or not? We still have product rules, okay? We still have product rules here. But for 4 and 5 here, why we split it up? What can you play around with vectors? How you combine two vectors? How many multiplication you can take between two vectors? Either you can do scalar product or either you can do cross product. These two are different. Why are they different? What happens if you take dot product between two vectors? Yeah, you will become a scalar value function. Okay, you will produce a number. But if you take cross product between two vectors, you produce another vector function. Okay, so you can see that in both cases here, product rule still works. It works. Okay, with respect to cross product and dot product still works. Obviously, you need to prove that, but I mean, we won't spend time on this. And the other thing is, how about if you compose with a scalar value function? What if you compose with a scalar value function? It doesn't make sense to compose two vector value functions here. Do you know why? Doesn't make sense to write like. It doesn't make sense to write like this. You know why? Yeah, so codomain of VT is not the domain for UT. Okay, so VTs go from R to maybe R3 already, but UT also go from R to R3. So these two doesn't match. Okay, so that's why it's natural to compose with a scalar value function here. So you have R to R and then R to somewhere else. And then luckily, luckily the chain rule still work here. Okay, chain rule still work. So if you are interested, you can try and prove them. Okay, using first principle. Okay, the limit function. So I have included some of them. Actually, no need to go to first principle. You can just use by assuming that these FTV, I mean, just assuming that your vector function are differentiable, then you can use what? You can use the property for your function of one variable. Okay, I'll give an example here. You can try and pursue yourself. Okay, do this. Okay, so let's quickly go through these examples here. So these examples here is not that I want you to know how to compute, but I want to show you that what's the significance of a tangent vector. Okay, what's the significance of a tangent vector? So this question says that if you know that your length of your space curve, or every point on your space curve have a length constant, then there's a very strong claim here. You know about the derivative or the tangent vector. Okay, the tangent vector is always perpendicular to your curve. Can you imagine this picture here? What does it mean by every point on your space curve has the same length? And then every tangent vector on this point is perpendicular to your curve. What happened? What can you draw? You can draw a circle. Okay, basically it's a circle. But in higher dimension, this is a sphere. So you always get an end sphere. Okay, so this is a very strong statement. If you know that the length, okay, of your point in your curve is always constant, then you always get a sphere. Actually, you always get a sphere. So how to prove this? Well, there's only one thing you can start. This kind of statement, statement is very easy because there's only really one thing you can work with. So you just start with what you have. So what does it mean by length of RT is C? This just says that the dot product between RT is C squared. But you want to know something about R prime T. How to go from RT to R prime T? What do you do? Differentiate. Okay, you just differentiate. So I think you should assume that RT is differentiable also in this case. I think there's an extra thing you need to assume that RT is differentiable. Okay, then you can differentiate these on both sides. And just now we go through how to differentiate dot product between two vector value function. So how to differentiate this? We can use the product rule. We use product rule. So what do we get? R prime T times RT plus RT times R prime T. So you just get 2 R prime times RT. But on the other side, you differentiate constant, you get 0. Also meaning that the dot product between these two vectors is 0, which is what you want, because you want to show that the two vector is perpendicular. So their dot product is 0, meaning they are perpendicular. Right? Because dot product equals to what? The length of the two vectors times cos of the angle between them. Yeah. So when is it cos theta to be 0? So it is when theta equals to 90 degrees. Okay. How about integral? You should guess. If differentiable, we can, if derivative, we can differentiate one by one. Integral, we should be able to integrate one by one also. Okay, also. Okay. And similarly, you can define arc length. Is arc length important? Yeah, arc length also quite important in the next chapter. So this is exactly what we have seen before. We have derived last time, right? how to compute arc length here. So we imagine as a how to measure a random curve in R3. We start by measuring the straight curve. A straight curve, how to measure? If it's horizontal, it's easy. You just put it on the ruler. But if it's not horizontal, what can you do? Well, you can tell me, 老师，你把你的尺弄弯一点就好。If my ruler have to be horizontal and vertical, you use what? Pythagoras theorem. Okay, so you use the horizontal square plus the vertical square is equals to the hypotenuse square. Then you can get the hypotenuse. But my curve is curvier. Okay, it's not straight. What to do? Last time, what did we do? We use a bunch of right angle triangle to estimate the curve. Hey, 可以想象我在讲什么? You should start imagining what I'm talking about because last time I draw it to you. So if you have this, then you can use a bunch of triangle to estimate your length. So you can see that this is really estimating. But how to make the estimate close? You should make your triangle smaller and smaller. Okay, so this is what we did here. Okay, so using dx over dt squared plus dy over dt. Okay, so if you are still interested or want to recall how we derive this, you should go back to the chapter of a parametric curve. We did that. Okay, we did that last time. So similarly, in the 3D version, you just add another derivative in dz over dt. Okay, so what's inside here? So we learn a new language today, right? It is the tangent vector. Okay, we learn a new language here. Actually, this thing inside here is the length of the tangent vector, correct or not? Because what is r prime t here? So okay, so let's restart. So rt equals to xt, yt, and zt, right? So every coordinate depend on function. And then how do you differentiate vector function here? You really just differentiate coordinates by coordinates. But what are these? X prime, y prime, z prime. This is really just dx, dt, dy, dt, and dz, dt. So what does it mean by taking square all of them and then add them up, take the sum and then take square root? This is just the length you learn in linear algebra. Okay. So there's another meaning for this arc length now. So what is it? It is just adding up the length of your tangent vector. Okay, adding up all how the tangent vector can evolve. Adding up the length of the tangent vector evolve. Then you'll get the actual length for your curve. 你不觉得很神奇吗？我看你的速度在每一个点，我就可以知道你走了多远。那又很合理，是不是？我看你在每一个点的速度，我就可以知道你走多远了，是吧？是不是？ I mean, if your speed doesn't change, right, it's easy to see, right? Let's say I just move 20 km per hour. Then the question asks, what's how far you have moved after 1 hour? 20乘1 20 km you move. Use velocity to determine your displacement. But let's say my speed is varies, then what do? Then you need to use this kind of integral method to do. Okay? Yeah. Okay. Okay, let's continue. Should we continue? Let's see how much more. Yeah, okay. We can break here. Later we'll start a new part about velocity. Yeah, there's one exercise on this arc length you can try. It's really similar to what we did last time. Okay, so let's take a should we take a break? Oh, okay, before break. So there's one thing called arc length parametrization. Have you hear about this before? Arc length parametrization. Yeah, arc length reparametrization. 听过吗？没有听过，没有听过啊。Okay, I think this is kind of important. So this is kind of important. So okay, let's briefly go through this. Quickly go through this. So there's one thing called arc length reparametrization. So what's the use of arc length reparametrization? So I'll tell you what is being used first, and then I'll tell you what to do with it. So what is arc length reparametrization is? Uh, well, the last time I told you, right? If you are given a curve in R3 or R2, you can have different parameterization. Okay, different parameterization maybe correspond to the speed. Okay, you can increase the speed. Increase the speed correspond to increase the scalar that you multiply to your variable. Okay, or you can take negative of your variable, meaning you change the orientation. Okay, but this function here, okay, so where's the arc length? Where's the arc length? So arc length is st here. So arc length is a st, and then if you obtain this st here, so this st one is can I zoom in a bit? So this xt here is not a number. Why is it not a number? Because this integral here just start from a to some undetermined time. Okay, so this is a function. And if you differentiate it, obviously it is the length of your tangent vector. Okay, so what does this thing can do for you? Okay, let's see this example here. So let's say this question asks you reparameterize this helix with respect to arc length. So this helix, we have seen it before. Have we seen it or not? Ah, yeah, we have seen it before. So this is a circle, but you can see that the points has an increasing height, okay, with respect to t. I mean, in the z direction with respect to t. So if you do this ds over dt, what do you get? So meaning you compute the length of your tangent vector here is always constant, constant with square root 2. So no matter what t you pick, every point the velocity is have, or the speed, because after taking modulus, you don't have direction anymore. Okay, you just have speed. I mean, tangent vector is a velocity, but after you take length, it's just a speed. So it's a constant speed of square root 2. And if you compute x, okay, the arc length function here is a constant gradient time t. Okay, so meaning what? Meaning this time, the length here is at any time a factor of square root 2. Okay, time of square root 2. So what does it mean by reparameterization here? So what do you do? So you sub the new variable here. So how to pick a new variable here? So the new variable here is this t, okay? And the s variable here is your old variable. So what do you do here? So you sub the new variable into your, sorry. So you change your t into x over square root 2. So what's the advantage of doing this? What's the advantage of doing this? If you repeat the process, you do this DSDT methods again, what do you think you will get? Huh? What do you think you will get? If you do repeat this process again, you treat these Rx with as a vector function again, what do you think you get? If you do this ds over dt business. So meaning you differentiate all these and then you compute the length. What do you get? Differentiate all these and then compute the length. You quickly do in your mind the calculation. Just 1 over square root 2. 1. You should get 1. You should get 1. You should get 1, right? Can you see that you get 1? If you differentiate all these and then you compute the length, you should get 1. Because the purpose of dividing this square root 2 here is to cancel out that square root 2. Okay, so reparametrization here means what? You make your speed 1. Okay, you make your speed 1. So after parametrization, this curve still curve out the same curve, but you can see that with different s and different t, they reach the same point. Meaning what? You change the time they reach the same point. If you change the time they reach the same point, meaning what? You change the velocity. But how do you change the velocity? You change it such that the speed is 1. Then you change it such that the speed is 1. Okay. So this is what called by the arc length. You change such that the speed is 1. You parameterize your curve such that the speed is 1. But how do you do it? Obviously, you need to start checking what's the speed you get first, and then you change based on that speed. Okay, any question? Yeah, I computed for you here. Yeah, I'll write t time. Okay, so arc length parameterization, reparametrization makes your speed 1. Okay, so let's take another break until 11:07. Hello. Oh. And it seems that your final exam timetable is out. Out, is it? Just out. Yeah, same time. So just got it. 第2个星期啊。OK，这样有时间读哦。晚上？哦哦，说，因为现在课室真的是不够用，很乱。然后我们的老师本来只是可能要 extra invigilate 给我一个，现在要2、3个。这个总共我要 invigilate 5个还是4、5个？啊，连着去啊？你们连着去？我们要连着去。1、2。不一定要第2是整个礼拜。1、2哦，就挤在第2个星期。还有会长，就会长，有次聚会长聚会。哦，有3个在一起。OK， 怎么在聚会上？最后一天。啊，对，就probability。OK。怎么在什么地方考啊？有没有跟人家一起考？2个额外2个点。哦，2个额外2个，我的嘞？哦，哇，所以是跟别人一起考。对。20 F4 啊？哦，F4 G02啊？对，G05。OK。 Mm. Oh, I see. Okay.
但是6号当时往反面就搞。
对，这个那么重要，我这那个不是我不能信啊。给你的时候，保证让你自己。为什么就是你让我睡在我床？没有没有没有，我保证3个小时到给你。到底说你要真的没这样努力的，这里这样子，我明白。
Just now, humble and Changyun come late, right? Just now we say that you can start submitting your project 2 topics starting this weekend. Okay. Okay. For the last part of these phase curve, actually is a application in physics or the real life about the velocity and acceleration. How do we understand the tangent vector, and how do we understand the derivative of a tangent vector? Again, double derivative. So you can notice that whatever you learn now, you only differentiate up to twice. You only differentiate up to twice. So these two have a meaning in physics. So if you compute the tangent vector, it is the velocity. If you compute the derivative of the tangent vector, then it will be a acceleration. Okay, so maybe it's worth to go through this topic so that you have some ideas for your project too. Okay, so well, actually there are concepts that we have been talking about, or you know, is that if you take the length of your velocity vector or the tangent vector is the speed. So what's the difference between velocity and speed? If you take physics before, then what's velocity? Velocity is a magnitude with direction, but speed is just the magnitude. Okay. Hey, I'm not sure. If you come from outside, your science or physics or not? Do you learn science? No more science. 没有咩 ？SPF 都有 science 呢？没有啊，中考没有 science 的，不是它没有一门那种，完就包完所有的科学。
未来要进行
哦，所以之前语系都没有。
初中
有啊，初中会学到 velocity 跟 speed。OK， 也不用学太多，我只想要你知道，一个是有号码 with direction， 一个是号码吧。我只要你懂这个吧。OK， 不用紧 ，it's OK。Only thing I want you to know about velocity and speed is magnitude, but velocity is speed with direction. Okay, so velocity vector here, the vector, okay, tells you the direction. How to get the speed? You just take the magnitude, the length, 长度是个号码嘛 so it is a speed. Okay, I think this one is kind of boring, so let's skip. This one, feel boring. Okay, how about this one? So this question is actually a very standard question in physics. So let's see how it works here. So This question is really phrased in a physics form here. So it says that objects have a mass move in a circular path. So whenever we talk about circular path, in circular path in maths is what? Circular 要符合什么条件？圆圈。Okay, radius 一样。Equation 呢 trigo equation what has to satisfy? X squared plus y squared equals to some radius squared. Okay. With a constant angular speed here. Okay, omega. So it tells you the vector function here, which is a cos omega t plus a sine omega t. So does this vector function satisfy a circle equation or not? Satisfy. So if you square the both coordinates, what does it equal to? Equal to a squared. So a is the radius. So 这个题目很聪明啊，或者这个 physics 很聪明啊，他把那个里面 scalar 那个东西叫做 angular speed. Okay, meaning if you change this omega, your curve will move faster. Okay, your curve will move faster. But 等一下我再说你另外一个东西。Okay, find the velocity and the acceleration of the object. Also find the force acting on the object. Okay, 先 determine 一下它要我们找什么。Velocity meaning find what? The tangent vector. Acceleration, the derivative of the tangent vector. So differentiate 一次 differentiate 两次咯。But force force 有没有学过 ？Force equals to ma. So a is the acceleration. Okay, so let's compute it. If you compute the tangent vector, what do you get? Negative a omega sine omega t, a omega cos omega t. So if you compute this speed, what do you get? Speed of this velocity. What do you get? Square both sides, right? Square both number and then take the sine and square root. What do you get? What do you get? A omega. Speed is a omega, but it says the angular speed is omega. 怎么有差的这两个 speed? Can you think about it? Why is it different? 为什么啊 ？Angular speed 跟 speed 怎么有差的？啊？啊哈，然后继续讲多一点。嗯，啊啊啊哈，然后就这么这两种 speed 是不一样的。为什么要除以 radius？ 哦 ，OK，definition。OK， 所以现在我要问的一个问题是，其实为什么要做这样的 definition？ 为什么要做这样的 definition 呢？为什么 speed 不够，还要做一个东西叫 angular speed？ 再转啊？
找这个
哦，它哦 ，OK，向心力 ，OK，and then any more？ 啊？什么？这是什么？没有，你可以没有知识的，因为我也没有知识，我们就纯讨论吧。为什么这个人要做这样的东西？然后我们就想一个比较合理的逻辑来推断，对吧？反正数学应该要做这样的事情，把全部东西就不合理的还是合理的东西都给它推出来。啊，还在说什么？因为它的 force contain 一些 factor on 这个 coefficient of 那个 t， 对不对 ？Then they will call this angular speed. So you could notice that if you compute this speed, this speed here will depend on A and omega. Let's say if you don't change your omega, your angular speed is the same, but you draw your curve larger. This will also increase the speed. So if you keep your angular speed the same, but your radius increase, your speed will increase. Okay. Okay. So this is another factor to control the speed of your curve. Okay, this is another factor that control the speed of your curve. They call it omega here. Okay. Okay. But there's one interesting thing here. You see, when you compute MA, second derivative of, but turns out that this formula here only depend on your phase curve. It just depend on your phase curve. It turns out. And then obviously with your mass, but there's a factor omega coming up here. 2 times coming up. Okay, omega squared. So the twice differentiable here become this square of some scalar number. Okay. Okay. Yeah. And then just depend on the position on the curve. Obviously, there's a mass up because mass time acceleration. But the nice thing is the acceleration just become the square of a constant time the position where you are at. That's all. And then why is it negative? Physics people come up with an explanation of that. Negative means the force is coming towards the center. Is it? 是吗? Coming towards the center. 如果我没有记错的话，向心力嘛，对不对？ Yeah. Okay. Come toward the center. Okay. Okay, coming to the center. Because potentially 如果你把东西丢，它就飞出去了嘛。但是问题是这个是会绕着那个转的，所以一定有东西把它拉回来。You understand？ 通常你把一个东西这样丢，它就飞走了。这个是会绕着它转，意思说有东西在拉着。它本来可能它走，可能它就走掉了。你知道这个东西叫什么吗？如果它转到一个程度，它跑出去。你可以转到快到它可以让它跑出去，这个东西叫做 escape velocity， 它可以逃脱这个拉住了它的。Okay, this is how the rocket also use this tool. For example, Elon Musk. What does Elon Musk want to do? Elon Musk want to fly to Mars, but Mars is very far. Very far 怎么办呢？可是飞 to Mars 的时候，它不只要飞过去，它还要飞回来，所以怎么办？还要几次的去补它的燃料。He has to fuel his rocket. So how to fuel his rocket? So rocket 飞出去过后，它还要再送一个燃料箱出去，在外面给它接起来。Because first time when you go out, you need to use up the fuel already. Then finish the fuel how? 丢掉它，让它回来，然后再飞一条出去接住它，等要用的时候燃烧。都要做几次哦，好像打油的工作啊，打油嘛，你车没有油了不要打，对不对？Yeah. So most of the time when the rockets fly in space, actually it's not using fuel. They use just a momentum. Otherwise, it's too cozy and then you cannot do it actually if you're gonna fuel for all journey. So only when you want to change direction. 你就烧一下 ，change direction 烧一下 ，yeah. Okay. Okay. So this is our topic. Maybe you can do in your project too. Tell us how Elon Musk. Hey, Elon Musk has a breakthrough. You know, Elon Musk has a breakthrough. has a breakthrough because he can recycle the fuel rocket. So after use it, then the fuel rocket get thrown back, and then the fuel rocket he can kind of capture it back， 可以 recycle 的，可以再转 fuel 进去。最近的新闻罢了，有看过吗？有没有看过吗？Yeah, the commentator state that is like a chopstick capturing the rocket。没有看过啊？谁看过？几个人看过？谁看过？就一个吧。我找一下，几点啊？11:20，我没有时间。看一下，这个蛮重要。Maybe you can talk about it in your project. Yeah, this one I think. Actually, he fell from 2014好像2014年失败，一直到今年才成功。所以不要以为你现在失败是什么大事，你要一直 try， 一直 try， 一直 try， 而且这个已经 take 了差不多9年了。你觉得你愿意吗？花9年去面对你的失败？Sorry，不是钱，还没其他失败，对不对？哎，等一下我看一下。Okay, I think you. 来看还有 chopstick， 来形容那个，其实是很大的一个东西，这个台。
In fact, at a live site where it was caught by a mechanical chopstick. Well, there were mechanical chopstick farms. They maneuvered the SpaceX beam as critical to its goal of making that rocket fully.
对啊，虽然他讲 chopstick 那个台其实是很大的一个台来的，而且这个他叫它 booster 是他就 boost 它飞了，然后让它掉回来。它掉回来的时候是没有开火的，自由落体的 ，free fall 没有开火的，一直到要靠近那个台的时候它才开火。为什么要开火呢？它要 adjust 到那个位置过后才慢慢再关火，可以找到。Maybe you can talk about this 我觉得他有在用 AI 的东西不然他怎么去量那个东西？怎么量那个距离？OK 了。Yeah, maybe you can talk about this inside your project. 他怎样做到这件事情 ？OK，Yeah, I think the rest. Okay, the one last thing before we left here, then later we will start with like the calculus. Is this question here? Let's say a projectile is a projectile is shot from the origin at an angle alpha from the positive x-axis with initial velocity v0. Assuming the air resistance is negligible, so obviously Elon Musk 不可以 assume 这个 Elon Musk assume 不了这个，所以他们一定要加一些 air resistance 进去。But in our case, it's fine. We just consider gravity. Then you need to find the position function of these projectile RT. So what's the value of alpha that maximize the range of T? So what this question is asking. So 他问你用哪个角度丢出去，丢出去 ，such that 你可以丢到最远。Okay, you can get the maximum distance here. So well, how do you do this? How on earth you gonna do this? How on earth you gonna do this? Any idea? Okay, like what I say. 数学题目是这样的，给你什么你就应该先用什么。What is given? Gravity. Gravity is given. So So gravity represents what? Represent acceleration. Okay, acceleration. So how do you get from acceleration to displacement? 怎么从 a prime prime 去到 displacement？a prime，他说 a or a，you need to integrate twice. Okay, in our case here, so you do the twice integration, and then what do you get? You get this bunch of vector function here, but there's a lot of coefficient to determine. So how to determine this coefficient? You just apply your boundary condition here. So what's the boundary condition here? You start where? T equals 0 at 0, 0. So you check whether this vector function really give you that point or not. Then you need to determine what's your coefficient here. In the end, what do you get? So in the end, you will get this answer here. X equals to V0 cos alpha t, y equals to V0 sine alpha t minus half GT squared. So what's this answer enlightening you? How this answer enlightening you? 它告诉你什么？This trajectory function here really depend on the velocity and the angle you throw. OK， 比如说他们丢标签啊、丢铅球啊，还有丢什么的。So it really depends on 它的 initial velocity and the angle it throws it. OK， 你有看过吗？你看过人家丢铅球啊？你们有运动会吗？有参加运动会吗？他们不是有 before 丢，不是要准备一下对不对？对吧？有些很多 pattern 哦，对不对？看过了，我看过我的朋友啦丢，好像要转几圈啊才丢出去了，有些或者有些就这样就丢了哦。Right? So how to get the V0 is really depends on there's a lot of skill you can use. Okay, but as long as the V0 is large, the alpha is giving you the largest value, then you are good. 你不可以丢太高，你也不可以丢太低啊！你要丢到一个中间的。最大的在哪里啊？我看一下有没有算过。因为这个答案好像不完整的，给我看一下。这个答案不完整的。下面是一些我跟那时候教 AIT 的时候讨论的东西。I mean the answer is out pi over 4 啊 ，pi over 4是什么角度啊？45 ，yeah, you have to throw at a 45 degree. Yeah, okay. But in real life, it's a 3D, so you need to be careful. Here is just 2D only. Real life is 3D, so you can extend this project to 3D if you like. Why I got these 2 pages here? When I first discussed with the AI students, we instead of taking the largest, we mistaken the question such that instead of finding the largest D, we find the tallest maximum point here. But it turns out that they are the equivalent question. So this maximum point, if it is the highest, it will also determine the largest D here, actually. So this is what we discuss here in this section here. So actually the highest point here will also tell you the largest D. So I plot it out here. Okay, so the solution is here. So if you are the 45 degree here, okay, you can see that away from this 45, they are quite symmetric. So for example, how to say, if you take alpha I, which is less than 45 degree, and then you take the other angle, which is 45 plus alpha I, they will have the same distance D. Okay, even though the maximum point is different, but they will drop at the same way. 有没有看过啊？不知道你们有看过卡通吗？看过卡通，好像有些人好像丢很高，掉在那边，但是有些人掉很低，也是丢在那边。So this is the calculation that show it. Okay, so although 你会觉得说，我觉得我要丢很远，对不对？我丢越高越好。It turns out that it's not true. Okay, if it is greater than 45 degree, although you can throw to a high point, but 你跟这个丢矮的人丢的地方是一模一样的，其实。Angry Bird，对 Angry Bird，对 Angry Bird， 有人玩过 Angry Bird 吗？现在好像没有 Angry Bird 了，不是？还有没？啊呀，我小时候玩的呀，Angry Bird 对。你以为你丢很高，其实你掉的地方是一模一样啊，跟你丢矮的地方。所以这个是这个计算我们算出来哦。Yeah，actually yeah，对，OK，就这样哦。OK，那有问题吗？Yeah，Angry Bird 对。现在还有 Angry Bird 吗？有啊。它是更新了还是旧了？还有第二代。OK。Interesting，很久没有看到人家玩了。Angry Bird。我们以前还有玩什么 Facebook game 叫蛋蛋糖，不知道你们知道吗？还是只有凯伦懂啊？暴露身份，你知道玩哈？蛋蛋糖，就是这些东西啊。Actually, when they design this game 啊，他就是把这些算法丢进去罢了。就是把这些算法丢进去吧。So that's why you can see this. 他就是把这些算法丢进去。Okay, if you're interested, you can go through. We won't test on this. If you are interested, you also can do it in your project. Maybe you can do the 3D version of this. 3D 的 3D version of this. This is just 2D. You can do 3D. I believe it's similar. It's similar. Unless you're gonna throw like ellipse, 就是秉承要做的东西了。At least, unless 如果你都是 throw 这样的话，就是在一个 plane 上面。可是还会 depend actually will depend on the gravity because gravity is always vertical. So once your plane gets slanted, then there's a 3D involving. Yeah. Never mind. You can do. Okay. Okay. In this last half an hour, let's start vector field. Okay, let's start a bit of vector field and then we'll continue next week. So vector field, where we do vector calculus, is really, really important. Okay, so this one, let's start new. So let's motivate vector field a bit. Well, so what's a vector field? Before we do a vector calculus, let's motivate vector field first. So what's a vector field here? So this is a function again. Okay. Again, from where to where? It's more general now. It's from Rn to Rn, but the n here will be the same. Either R to R, R2 to R2, R3 to R3, R4 to R4, R5 to R5. But in our case, we will stop at R3. Okay, so we will just stop at R3 here. So usually we will look at R3 to R3 or R2 to R2. So meaning what? Meaning, let's say in R2 here, given a plane in R2, and given every point in R2, what should you give me? You should give me a vector. So on every point, you will attach a vector here. Okay, on every point, you should attach a vector. Something like this. Maybe you ask, 有什么用啊？放一个箭头这样。Okay, if you study physics before, one place you'll see this is about magnetic. 有看过吗？这好像小学都有看过吧 ？Magnetic. Okay. So magnetic. What does a magnet do? Attract or repel. Okay, if I put n and x on side by side, what happened? N will get attracted to x, or x will get attracted by n. That's why you will draw arrow like this. Then this is a vector field because this picture is drawn in R2, and then you can see that with this, the starting point of this vector is just a point in. So you have a point attached to a vector. Okay, yeah. What else? 你们每天起来有没有刷牙啊？有刷牙吗？有冲凉吗？ Okay, so if you look at your basin 还是你有大便吗？ If your basin or your 叫什么那个 tank, right? near sui, when your water go into the sink, I mean the sink place here, you will follow a flow like this. Either spiral flow or what. So this, you can imagine that there's a direction on each point here. Okay. Inside the water. Okay or not? Yeah. At each point you can put this vector and then follow the direction of the flow. Okay, so you describe a flow. This is what I want to say. Okay, we could describe a flow. Magnetic is also a magnetic flow. Okay, so you describe a flow. So this vector field is to describe a flow. Okay, let's look at the definition now. So what's the definition here? So let's say just look at vector field on R2. So the notation here is, if I say vector field on R2, you should immediately think that this is a function from R2 to where? To where? R2 must be the same end. Okay? Whenever we talk about vector field, it has to be the same end between domain and codomain. Okay? If I say vector field on R3, is a function from R3 to where? R3. Okay, must be the same end whenever we talk about vector field. Okay, so let n be a set in the R2. What is a vector field? It's a function that assigns every point in xy in the domain a vector. Okay, a two-dimensional vector. Similarly, if it's a vector field on R3, on each point we will attach what? Attach a vector in R3. So, well, I mean, there's a natural way to attach vector, right, in R2. You know that there's a natural way to do it. Every point on this R2, right, it serves a vector. So there's a natural way to put a vector field on it. So namely what? If this point is x1, y1, you just put x1, y1 vector on this point. In that case, what kind of vector you get? The vector you get, 中文叫做发散的 is like divergence，像什么啊？像榴莲这样，当然会像榴莲嘛，每个尖尖都是向外的。OK，maybe、你觉得这个不太像，如果放在 R3 更像了。If I just put the vector as the point, then every point has the vector going out， 出去，对吗？想象得到吗？想象得到吗？会去听懂我讲吗？重复一下。R3 的 vector 是向外 ，R2 呢？R3 的什么 vector 是向外的？Okay, good. XYZ is the point on your R3. Okay, 它是向外的。Okay. This is very important. Later we'll talk about an idea about divergence. Okay, divergence. Okay, so let's try one exercise. So fxy equals to minus yi plus ixj. Is this a vector field or not? 是不是给一个 R2 点会给出一个 R2 vector 是吗 ？Okay, if yes, try and plot this vector. Okay, try and compute this vector and then plot out the vector field. Okay, 算一下 given this xy, what's the vector you get? And then how do you draw the vector field? 画一下，给你3分钟。 Okay, anyone finish compute these vector yet? So what's the vector correspond to 1, 0? 0, 1, and then 2, 2. If 2, 2, 3, 0, 2, 3, then 1, 0, so minus 2, 3, 0, minus 1, 2 minus 2, 0 minus 3, 1, 0, 2, 2, and okay, so let's pick some important point to look at first. Let's pick this 4 points. Okay, so if you pick these 4 points, what happened here? So where does this 4-point live? This 4-point live on a circle of radius 1 here. Okay, so on 1, 0, you have a vector 0, 1. 0, 1, how does it look like? It's a vertical vector here. Okay, 0, 1. And then on 0, 1 point, what do you have? Is a horizontal going to the left. So this is negative 1, 0. And then on the negative 1, 0, what's the vector here? It's going downward. And then on the point 0, negative 1, it is horizontal again, but in a different direction. Okay, notice that 哇，很多 bracket 又圆了，又尖了，又方了。怎么用这样多 bracket What's the difference between these brackets? Yeah, so usually for points, right, we will use a round bracket. Okay, for vector, either we use this angle bracket for column vector, or we use the this is row vector, and then either we use a square bracket for column vector. Okay, normally we just use a round bracket for point. Okay, obviously you can see it as a vector, but if you want to refer it as a point, we use round bracket. So what can you see here? Around this point, this vector field is like rotating. It's like rotating. If you pull out all of them, it is really rotating. Okay, it's rotating. You can see that when the radius get larger, the vector length get longer also. Okay, so you could imagine that if I put some point on this vector field, this point can follow the flow of this vector field here. Okay. Okay, so this is how you should imagine about this vector field. This arrow is trying to push things. You can try to push. Okay, so it will push your. If you put a particle here, it will get pushed by this vector rotational. Okay, let's look at different examples here. For example, this function. Yeah, this one is what I told you, right? Okay, but it's slightly different. What's the difference here? Just now I asked you to put x, y only, but here divided by what? What is square root of x squared plus y squared? Yeah, it's the length. So meaning what? I shorten the length of the vector, the image. Okay. How I shorten it? Until the length of the vector is equals to 1 in each case. Okay. So this is with norm 1 vector as going outward from this origin, and then there's another one going inwards, right? Okay, because this is exactly the gravity. Okay, going inwards. So how to go inwards here? So what they do they put a negative direction. Okay, how to go inwards? You put a negative direction. Okay, negative 过后就反方向。Okay, so going inwards. But here seems like divide more than the length, right? So they divide the cube of this norm here. More than the length. Okay. So you see what did you see here? 你看到什么？你会觉得牛顿的理论好像很伟大这样，其实就是从一个简单的东西来罢了，就从这个简单东西来罢了，给它方向转一转，哎，就变很伟大了。你明白吗？难的东西全部都是从简单的来的，所以你不要不会简单的东西就要去搞难的，你懂吗？你不要以为难的东西就是很难，他们全部都是从简单的东西开始想 ，OK 吗？很自然吗？刚才我不是告诉你很自然吗？我可以放 x y 在上面，连这就是往外面走的 vector。如果你想说哦，我要把东西吸进来，要往里面走，是不是放一个减就好？然后你就开始 prove 咯 ，prove 一大堆你想要的 property 有没有？哎，有哦，可以 work 哦，就这样咯。它就是放一个减方向罢了嘛。And then extra thing 就是要 check， 还 depend on 什么 variable？Maybe depend on mass 啊，还是还有一个 extra constant 呢？这个什么叫做 G 啊？也就是各种没有用的东西丢进这个 G 里面就对了。对啊，各种东西丢进这个 G， 哪里知道有一天这个 constant 要 split 去不同的 constant 呢？你明白吗 ？OK， 这样，所以难的东西都是从简单的东西开始想的，就是从一个很简单的 idea。So what we need to develop here or develop in the degree here is you need to start with ideas, start with definition, and then how to prove external theorem, proposition, property, different characteristic and property. Yeah， 这是你要学的东西，不是一来就学这个学来没有用。我也会学，大家都会学这个。问题是怎么去从一个简单到难的东西，这个阶段你要会，这个阶段不是所有人能做得到，但是这个 degree 可以做到这样子。OK， 从一个不懂的东西讲变到懂。OK，and then this is very variable 啊，因为你的老板就喜欢这个东西，你知道为什么吗？你为什么知道老板喜欢这个能力吗？因为通常老板只有钱罢了，会做，他只会讲，你明白吗？啊，会做又会讲又有钱的那个是很少的，可能比如 Elon Musk， 比如 Mark Zuckerberg， 但是大部分的老板就是很多钱吧，他可能很幸运就攒到这笔钱，但是他 idea 很多，他做不出，他就需要你了，you understand？ 你就要帮他讲这个 idea 出来怎样去实行这些 idea 咯。Then， 如果你做得出，你就是小老板了，钱就是你的了。You understand？ Yeah. OK. Continue. 有多少？哎，不用 continue 了。OK， 有什么问题吗？Okay, so far we can stop at vector field. Next time we can continue with vector field. Okay, if no questions, see you next week.